Oh, good afternoon, everyone. I want to welcome you to my lecture today. Just like what I said Monday, we're still going to use the material for Monday because we're going to continue from where we stopped. Actually, on Monday, we started application of Bayesian network, and I remember I walked you through uh, areas of application in real life, when it comes to Bayesian network. So without wasting time, I'm actually going to proceed to where we stopped the other time. Okay, we started computational example, and of course I need you to pay attention. Okay, now you're giving this network. Okay, we got 4 nodes in the network, A, B, C, D, and of course the conditional probability table are given. So this conditional, if you take a look at all of that, okay, that is what we call the CPT. So you already know the frequency associated with a particular node, and the question that we were trying to solve, uh, you know, we actually want to figure out the probability. Give me 1 second. So we want to figure out the probability of D given A. Okay. So if I want to figure out the probability of D given A, okay, what I'm going to do right now, I'm actually going to let me stop my share so that I'll be able to want to share the whiteboard, then I write on the whiteboard. Okay, so like I said, we want to find the probability of D given A, and the probability of that's going to be the probability of the joint divided by probability of A. Now we take a look at the numerator now. Don't forget, if you take a look, if you go back to the diagram given, you're actually going to see that, there's an event B, okay, that is between D and A, okay. That event may be observed and may not be observed. So there are 2 possibilities. So if I want to rewrite the probability of D, I'm going to write the probability DB A, okay, plus the probability D A B bar A divided by probability of A. Any question about uh how I write that? There's a B in between D and A, okay, and that very B may be observed and may not be observed, and that was why we put B there. Plus means or, so which means the numerator is a total probability. Does that make sense? Now, and I want to focus on, let me now examine this, what is probability of D, what is that? So I want to look at that, okay? Now, if I want to look at that, it's going to be probability of D given AB multiplied by probability. Take a look at that. If you look at the picture, D actually depend on B and A, right? If you take a look at the diagram. Okay, so if I want to rewrite that, putting into consideration the dependent law, I'm actually going to have that guy. Similarly, I'm gonna also, the one for D bar is also going to be this guy. Any question? The two are more or less the same, except B in one and B complementing other. Any question? Okay. Now, uh, the next thing I want to do now, okay, if you take a look at this and this, I want to write them in a different, if I have the probability of G given AB, okay, that can be written as, D, according to the picture, D actually directly depends on B, right? So I'm actually going to call that equal to that. This is what we call conditional independence. Okay, this is what we call conditional independence. Okay, now knowing information about A does not really provide the additional information. Okay, because D directly depend on B. So if I want to also rewrite the other one, I'm also gonna have this. Take a look at that. I'm also gonna have that. Now, if I have that now, what I'm actually gonna do, okay, let me say I want to plug that guy in here. Okay, I want to plug that in now. So this is gonna be D given that, and this is gonna be D given that. So I just plug that in. So plugging that in now, let me click in this guy. Okay, so when you take a look at what I have right now, okay, I'm actually having that, okay, on that. So if I put it back, if I write my probability of D given A, okay, it's going to be probability of D given B, the probability of that divided by probability of A plus the probability of D, or given that, the probability of that divided by probability of A. Take a look at that. Okay. I also allow you to take a picture. Okay. You can take a picture. That's no problem. Okay. And this is also being recorded. Now, I need you to pay attention to something. Take a look at this guy. Can somebody tell me what does that give based on what you've learned? This guy, these two guys. What is the ratio of probability of AB to probability of A? What does that mean? Can somebody tell me? That is probability of B given A. Do you see this? This over this. If you want to go by the law, that is the probability of B given A. If you have the probability of B given A, is actually going to be this divided by probability of A. So, which means that guy there, if I want to rewrite right now, let me look for space. So if I want to rewrite now, so I'm going to write the probability of D given A equal, okay, the probability of D given B, the probability of B given A, then plus the probability of D given B complement, the probability of B given A complement. Take a look at that. Now, do you know where we are now? We're super easy. Now, let's go back to what was the assigned probability in a question. Okay, in the question, what you're given in the question, you're given the probability of C given A. When A is true, its probability given to this will be this. The probability of C given A complement, they gave you 0. I'm writing what they gave you in the question. If you go back to what they gave you in the question, and the probability of A was 0.4. Then the probability of B given A is actually 0.8. The probability of B given A complement is actually 0.3. Then the probability of D now given B, give me 1 second. So the probability of D given B is actually 0.8. The probability of D given B complement is actually 0.3. Now, let us now, based on what you're giving, right? Let's take a look at that. What is the probability of D given B? This is going to be 0.8. That guy. What is probability of B given A? That's another 0.8. I've started substituting now. I started plugging in now. Okay. What is the probability of D given B complement? Okay. The probability of D given B complement is 0.3. Okay. Now, what is the probability of B given A complement is 0.3. Okay. Now, all we just need to do 0.8 times 0.8, that is 0.64, right? 0.64 plus 0.3 times 0.3, at the end of the day, your final answer is going to be 0.7. So I calculate the probability of D given A to be that. Any question? I'm done. I'm done finding probability of D given A. You see, the way it's done, it's very easy. Any question? Any question on this? Go ahead. No, the last one is not A. Look at that. Yeah, because something was occupied. You remember the other time we're talking about total probability, whether A is observed, A is not observed. So we work that all the way here. You remember before, where you have probability of B given A, what do you have there? You have the probability of B, comma A divided by probability of A. Where you have probability of B given complement A was the probability of B, comma A complement divided by probability of A complement. So if you follow the derivation that what I've written today, we actually find ourselves there. And the whole thing actually starts from the fact that probability of DA, okay, the probability of DA is the probability of D, B, A plus probability of D, B complement A. You see why the B complement comes in? Because this is a total probability, DA. If you look at the structure, what is in between D and A? B. That B may be observed or not. When B is observed, it is this. No complement. When it is not, it is this. So that plus is indicating, or does that make sense? Okay. Any other question? Okay, now I just wanted to say like that. We answer, we compute here based on the diagram. Now, another question that I want to solve now, give me 1 second, is what of you are still given the same structure. So what is the probability? Can somebody tell me for extra credit? If I want to find the probability of C, I want to find probability of C. Can somebody tell me what I'm going to do? I want to find probability of C. Don't forget, C depend on what? According to this structure, C depend on what? A. Oh, if I want to find probability of C is going to be total probability, where I'm going to consider when A is observed and when A is not observed. So if I want to write the probability of C now, are you surprised to see this? Give me 1 second. Okay, are you surprised to see this? Are you surprised? I want to find probability of C, but C depends on A. Now, the probability of C become a total probability because it's either it's either A is observed or not. Any question? So I may want to find the probability of C when A is observed. Maybe that very C may be the probability of somebody testing positive for COVID. And maybe A will mean disease is present. A complement may mean disease is not present, which means a machine can say somebody tested positive for COVID and disease may be present or not. Does that make sense? Okay, now, if you take a look at what I have now, I want to find the probability of AC. Oh, I want to find probability of AC. Of course, there's a connection between it. That will lead us to dependent law. Okay, now in the dependent law now, I'm actually going to have the probability of C equal probability of C given A multiplied by probability of A. That is the way to write that. Look at that. Why am I writing it? C depend on A, then multiply. That's a dependent law. Then I'm going to do the same right here. P, C given A complement multiplied by probability of A complement. Is that not easy now? I can start plugging in. What is my probability of C given A? You were giving, look at that, C given A, you giving. Just plug that in. 0.8. What is the probability of A? Okay, you were giving probability of A to be 0.4. Okay, you're going to plug in that. Then what is the probability of C given A complement? You can see, you're already giving all of that. What is the probability of A complement? You know the probability of A. Then the probability of A complement is going to be 1 minus that. So that's going to be 0.6. So if you multiply this by this, multiply that by that, you add them all, the final answer is going to be 0.5. I'm done. I'm done. Okay? That's how to do that. Very easy. Okay? That's how to do that. Okay? Now, based on that question again, I want to find what is the probability of A given C. Okay? I want to find what is the probability of A given C. Now, I want to find this. I want to find the probability of A given C. Now, let me ask you, in the structure, okay, in the structure, does A depend on C? No. That will in the structure, what you only have is C given A. Then here you're going to apply Bayes' theorem. If I want to find probability of A given C, it's just going to be, I will revise that. The probability of C given A multiplied by this, divided by the probability of C. Look at that. That's what I'm going to use. Because in this structure, there is no, A does not depend on C in the structure. C that depend on A in this structure. So if I want to find A depending on C, then I have to use, it's going to be that. That's a Bayes theorem. Now, we've already done all of this. What is the probability of C given A? They give you that they give you that here, 0.8. What is the probability of A? You're given is 0.4, right? Divided by what is the probability of C? That is what we just found. We found probability of C the other time, which was 0.5. So by the time you compute that, your answer is going to be 0.64. Okay, that will be 0.64. Don't forget, we found probability of C that time. C was a total probability, right? Okay. Now, I think that is done now. That's how we go about that. Now I want to go back into the material. Okay, I want to go back into the material. Any question before I go back into the material? You're good, right? Okay, so actually going to stop my share and I'm gonna go back to the material. Let me also share that. Let's see. Okay. Now we're done with that guy now. So we actually want to move. Okay, so we want to go into another example. Oh, let me see this guy. Yeah, we want to go into another example, and I need you to pay attention. Okay. Now, to safeguard your house, you recently installed two different alarm systems by two different reputable manufacturers that use completely different sensors for the alarm systems. Okay. Now, A, which one of the two Bayesian network given below makes independent assumptions that are not true? You know, there are some independent assumptions that are not true. Okay. So how are we going to know? Then all your explain all your reasoning. Alarm one in the structure means the first alarm system ring. Alarm two means the second alarm system rings, and of course, burglary means that a burglary is in process. Okay, now let's look at the structure now. Okay, uh, let me see. Um, wait a minute. I'm gonna see. Did I pull the structure here? Let me see. Okay, this is the structure. Take a look at that. Now, if you look at the first one, right? The first one tell us alarm one and alarm two. And the alarm is going to ring when there is what? Burglary. But the second one is telling a different story. You see that? The burglary, depending on the two alarm. Okay. The second, this one is telling us that when the alarm rings, the burglary is taking place. But this one tell us before alarm rings, the burglary is going to take place. Okay. So, but let me tell you this. Alarm one and alarm two. This one is trying to tell us alarm one and alarm two are independent without observing this. But this one is trying to tell us alarm one and alarm two are conditionally they are independent given event of burglary has taken place. This is only going to be independent from this given that. So, and that was why if you take a look at the what I said here. So I said the second one, firstly, I told you if you look at the second one, the parents were alarm one and alarm two. Burglary is the child. But we expect the parent to be alarmed. Why sorry, the child to be alarmed. Why burglary should be the parent? Like it is burglary that will tell you that we send a message to alarm system. Does that make sense? So if you take a look at it, I said the second one firstly assume that alarm one and two are independent if the value of burglary is unknown. No, they depend. Because what happens is what is going to force if alarm one rings, there's possibility that alarm two also ring. And something has already occurred before alarm one rings, burglary. But alarm two, the second structure didn't give that information. And that was why I said, however, if the alarms are working are working as intended, it should be more likely alarm one ring if alarm two rings. That is, they should not be independent. What is the meaning? They should not be independent. Mean they should be dependent. Does that make sense? Because one will trigger the other one to ring. And before one trigger the other one to ring, if an event of burglary has taken place. Now, that's all about that. Now, let's answer another question. Consider the first Bayesian network. We said we want to make it is the first Bayesian network that makes sense. okay, not the second one. Now, consider the first Bayesian network. How many probabilities needed to be specified for its conditional probability tables? I'm actually going to walk you through that now. How many probability? Then how many probability would be needed to be given if the same joint probability were specified in a joint probability table? Now, let me tell you this. Depending on the numbers of nodes that you have, how many nodes do we have in that diagram? The node means random variable, okay? It means alarm 1, alarm 2, burglary, how many? 3, okay? And we now need to consider what is the level of each variable. Now, alarm 1 is discrete. It has 2 levels. It's either it's a ring or not. Alarm 2, also discrete. It has 2 levels. It's either it rings or not. What about burglary? Burglary is also discrete. It's either there is burglary or no burglary. Now, in each of them, what do you have? 2 levels. Then, if I want to know the possible numbers of probability, that will be 2 raised to power the number of nodes, which is going to be 8. Then we now subtract 1. That is what I'm doing here. Take a look at this guy. Take a look at what I'm doing here. Now, do you now understand how I got 2 raised to power 3 minus 1 equal to 7? Because each has 2 levels. Each variable has 2 levels. And how many of them? There are 3 numbers. Then it's going to be 2 raised to power 3 minus 1, then equal to 7. That is the formula to know the possible probability of values. Now, but let me tell you this. That is a possibility. That possibility is when we are actually, if you go back here, take a look at the way it is framed. How many probability need to be specified for its conditional probability table? That's what we just did. Okay, that is 2 raised to power. That 2 is, we're only going to use that 2 if all the variables have these 2 levels. But what if one has a different level? We're not going to use that. You remember I was walking you through an example on Monday that has to do with professor writing accommodation letter. One of the variable grade has 3 levels. Does that make sense? Okay, so I'm going to tell you how that's going to be worked out. But what I want to talk about now is a situation where each variable has the same numbers of levels. Okay, the numbers of level raised to power the numbers of variable minus 1. Now, another question, how many probability would need to be given if the same joint probability distribution was specified in a joint distribution table? Now, we're actually going to be the one that will figure that out, and we're going to do that. It's going to be 5. How do I know it's 5? Oh, give me 1 second, sorry. How do I know it's 5? Please, I need you to follow this. If I want to know it's 5, I will only need to look at the structure. Okay, looking at the structure, what is the parent? The structure starts with burglary. Probability, I need to calculate probability of burglary. What is the next thing I can calculate? The probability that alarm 1 ring giving burglary. Any question? What is the next? Alarm 1 can ring even without burglary, because it could be maybe something else. And that was why we said, you said that you have burglary or not. Alarm 2 can ring due to burglary. Alarm 2 may ring even if there is no burglary. When you take a look at that sign, it's the same thing as complement. Okay? Now, how many do we have here? 5. Okay? And what is the total? Like, without looking at the structure, okay, if I want to base it on the numbers of variables, and I want to base it on the level within variable, it's all going to be 7 probability. But looking at the structure, it's going to be 1, 2, 3, 4, 5. Does that make sense? Okay. Now, the next thing I want to talk about, now, please pay attention now. We are going into computation. Okay? We are going into computation. Okay? Consider the second Bayesian network. Now, this computation now, we want to base it on the second Bayesian network example. So, which means it's still going to be the same thing, the same way we calculate probability given any Bayesian structure. Take a look at this. They give you the probability that alarm 1 ring 10% of the time and alarm 2 ring 20% of the time. You've been given this. Let me tell you this. Why is it that these are not conditional? Alarm 1, alarm 2, because I'm going to show you something now. Because we're focusing on the second one, where alarm 1 and alarm 2 are the parents. I'm going to show you, I'm going to go back to the structure now. We're considering the second one where alarm 1 and alarm 2 are the parents. What is that? When we're using that, who are the parents here? Alarm 1 and alarm 2. The process starts from them, right? Okay. And that is why if I want to start, okay, we're only going to be giving the unconditional probability for them. They are not conditioned on anything. It is burglary here that is conditioned on them. Does that make sense? Okay. Now, if you take a look at give me one, if you take a look at what you are giving. Now they give you this information, they also give you the probability of burglary, giving alarm 1, alarm 2 to be 80%, the probability of burglary, giving alarm 1 and no alarm 2, that is complement of alarm 2, you give it to be that. Okay. Now, which other information? And they also give you the probability of burglary, giving complement of alarm 1 and alarm 2 equal to that. And they also give you the probability of burglary, giving no alarm 1 and no alarm 2. Okay, you're giving all of that. Don't forget, all this they were given based on the fact that they want us to focus on the second Bayesian network in the example. Now, what is the question? They wanted to calculate this. I want to calculate the probability that alarm 2 rings, given that there's burglary and alarm 1 has already, already ring. That's what I want to find now. How do I go about this? I think I've explained here. I'm not going to take your time. Take a look at this. I'm going to show you. Now, this is the answer. What do I want to find? Please pay attention. What do I want to find? I want to find this probability. If I want to find the probability of something given this and this, okay, then I'm actually, if you want to follow this, if you want to follow, let me even write it here. If you want to follow, if I write probability of A given B, that is going to be the ratio of the joint over probability of B, right? But you know what I'm going to, here, the probability of this given these two, okay? It's going to be, I'm going to consider the ratio of what is going to be the joint, all of them. This is right here. Do you see that? Do you see that? Then divided by what? Divided by the probability of these two here. Which means this is more or less, so which is more or less like, take a look at this guy now. If I have the probability of A given B, C is the same thing as probability of A, B, C over probability of B, C. That is a generalization. That's what I'm doing. That's what I'm using here. Take a look at that. Do you see that now? That's what I'm using. The probability of A given B, C will be the joint. We consider all the joint divided by the probability of the B, C. The one the event was conditioned on. Now you understand that now. Now, if you take a look at this, if you now take a look at this, the numerator, you see the numerator, right? The numerator is the probability of the joint, and that will come from the graph. You remember in the graph, if you want to look at the graph, it's going to be probability of alarm 1 times alarm 2 times probability of the burglary given alarm 1 and alarm 2. We're talking about the graph. Okay, and that's exactly, okay, what I'm doing here. Do you see this guy? So because I want to find the probability of the joint occurrence of all the three, then I'm going to look at the structure, then I'm going to write this guy out. When I write this guy out, okay, what is it? And don't forget, you'll be giving probability of alarm 1 to be 0.1, alarm 2 to be 0.2, and the probability of the burglary giving alarm 1, alarm 2 to be 0.8. If you multiply that, this is what you are getting. Now, what have I obtained now? I only just got this, which is just a numerator, here. I just got the numerator now. Then after getting the numerator, okay, if you see what I just get now, the probability of that is this is the numerator. Now, the next thing that I actually want to do now is to find this guy. Take a look at the guy. Probability of alarm 1. Okay, this. Now, if you take a look at what I have here in the numerator here, alarm 1, alarm 2, and burglary. Okay. Now, if you take a look at here, you're going to see that what I have in the numerator can also serve as a total probability. Where here, what is observed? Alarm 2 is observed. And here, alarm 2 is not observed. Do you see that? Alarm 1 observed, alarm 2 observed here, and alarm 2 is not observed here. Then I'm also going to use the pattern. I'm also going to use that structure again, except that where I have alarm 2 is going to be the complement. So this and this are more or less the same. So when I plug in all of that, I'm going to have this guy. I'm going to have 0.056. Now, after getting that, then I can now, why do you think I got the first one and the second one? Because don't forget, this one here is the denominator to what we want to find. And that denominator, okay, where is the denominator? I'm going to show you now. The denominator to the question that we want to find. Can you see it here? This denominator is a total probability. Why is the denominator a total probability? Here, when I want to find total probability, do you see, is there any alarm 2 here? We're going to consider total probability where alarm 2 is observed and when alarm 2 is not observed. So focusing on the denominator now, okay, that is the reason why I'm doing that. So now, if you go, you're going to see the denominator now. Now, what do you see? What do you see here? Denominator is a total probability where denominator, where alarm 2 is observed and a situation where alarm 2 is not. And don't forget that you will use the structure to find the probability of this joint. You will use the structure to also find the probability of this joint. Then what are you going to do? We're adding them together, and we've already obtained them here. You see the two? We've already is this 0.016, 0.056? That's what we're going to add. And the moment we add that, we got a 0.072. That is a denominator to what we want to find. So if I take you to so now this is a denominator to what we want to find. So what we want to find now is now going to be the numerator that we got the other time divided by this guy. Okay, then that will give you what we're looking for. Now don't forget, this is what we're looking for, and that was why we got this. I've already plugged in 0.072, you see, then is 0.016. So which means 0.016 is included in the 0.072 because the 0.072 is a total probability. I'm done with that. Now, because of my time, I got 10 more minutes. I want to move to the last one. Now, please, this time around, I want to go to healthcare. This example is very simple example. I want to go to healthcare. Okay, consider the following Bayesian network where F having the flu, and C, coughing. You know, having the flu, that's a disease, right? Then coughing is a symptom. But let me tell you this, somebody can cough and may not have a flu. Could have something else. But if you take a look at this is a very simple structure. Take a look at this structure. What happened here? Having a flu depend on coughing. What is the probability of having a flu in general? Is 10%. Having a flu here is a parent. Okay, if you take a look at sorry, it's a child. Okay, so now I wanted to take a look at what I actually have in here. If you look at the direction of the arrow, C depending on F. C is trying to say, oh, when I'm coughing right now, I may be having flu. I'm going to say that again. This is a child. C is a child. F is a parent. You know, depending on the way, based on this structure, at time this one can be here, this can be here. But based on this structure now, if I'm coughing now, maybe I have a flu. Now, there are two possibilities. Don't forget here, how many levels? It said that you have a flu or not. 2 levels, right? Now, and then it said that somebody cough or not. That's another 2 levels. And that will be 2 times 2. On this, we're going to have 4. Now, take a look at this. You'll be giving this guy. This is the probability that somebody that is coughing has a flu is a 0.8. Probability that somebody that is coughing and do not have a flu is a 0.3. You've been given this. And what is the question? The question says, write down, please, I need you to be focused here. Write down the joint probability table specified by the Bayesian network. How do I write this? I'm going to write it based on, when they say joint, what do we mean by joint? The joint occurrence. How many events? Yeah, F and C. It's going to be F, C. Now, we're now going to consider possibility. First possibility will be true, true. What is the meaning of true, true? The true, true is this one. Okay? The true, true. Now, it means somebody is coughing. Somebody have a flu and is coughing. Somebody have a flu and is coughing. Okay? Now, if I want to consider that, I'm going to take a 0.1 from here. Okay? So what do you think I'm using here? Oh my God. PF multiplied by C given that. That's what I'm using. What am I calculating? I'm calculating the joints. You see that? That's what I'm using. Here is going to be, so here now it's going to be when the flu is true, I have flu. Okay? And it is true that I'm coughing. You can see it here. So when you multiply that, that gives you 0.08. Okay? Now, another possibility. Okay? I may have a flu, but I'm not coughing. Now, in that situation, I'm going to take true from flu. It's still going to be 0.1. But I'm not coughing. Please pay attention now. Where do I get the 0.2? Pay attention now. You know, this one is, I'm coughing, given that I have a flu. Now, in that situation, I'm going to do this. I want to find the probability of C complement given F. That is 1 minus probability of C given F. Does that make sense? That is what I put here, which is going to be 1 minus 0.8. Please write down the formula. The probability of C complement given F equal 1 minus C given F. Okay, that was how I got the 0.2. So multiply 0.1 by 0.2, that gives you 0.02. That's another possibility. Let's go to another possibility. Okay, I don't have a flu, but I'm coughing. I don't have a flu. What is the probability of not having a flu? It's going to be 1 minus this, which is going to be the complement of that. That's why you have 0.9. Okay, you see that? Then multiply by the probability that I have a cough given flu, 0.3. Okay, so we're talking about this guy now, true. Okay, that gives you 0.027. Then I don't have a flu and I'm not coughing. I do not have, this for me false. Okay, what is the probability I don't have a flu? It's going to be 1 minus this, 0.9. What is the probability that I'm not coughing? Okay, now I'm not coughing. Okay, now which means I want to consider a situation where C is complement. Here, there's no situation here where C is a complement, right? If you take a look at what I have. So it's going to be 1 minus this. So which means the probability of C giving F complement, okay, is the same thing as 1 minus probability of C giving F complement. Now, I told you the other time, what you're going to have is going to be the same in the condition. If this is complement, the condition of that one also going to be complement. The only difference going to be, this is going to be complement. The other one is going to be the C. It's going to be the, you understand what I mean? So how do I got the 0.7? I got the 0.7 for false, okay, which is actually going to be 1 minus this guy. What is 1 minus 0.3? That will be 0.7. When you now, I've already set up the table. This is the joint probability table. Now, based on the joint probability table, they're going to ask another question. Please pay attention. What is the probability of C? We can use the table to get the probability of C. The probability of C, okay, is actually adding this guy, okay, to this guy. Now, what does that mean? You can actually cough, you can cough and have a flu, or you cough, you don't have a flu. That's a total probability. That's why you are adding them. Any question? With the table that you have set up now, it's going to be super easy. Do you see that now? Okay, which is that probability of C, because C depend on F, is the same thing as having CF plus C complement F that I wrote you at a time. And what is that of CF? Okay, what is that? So the one of CF is 0.08. The one of CF complement is 0.027. And you know what? The moment I know the probability of C, I can get probability of F given C. Now, wait a minute. This is similar to what we did the other time. Does F depend on C? Does F depend on C in this structure? Yes, right? Now, I can use the idea of a joint of a conditional probability here. Are you surprised? That's a normal thing, right? The probability of F given C is going to be a ratio of the joint divided by that. Now, what is the joint? It's 0.08. The one for true, is 0.08 divided by the probability of C, which is the total probability. Then I can also figure out what is the probability. I can also figure out what is the probability of this guy. There's no difference between this and this, except that where we have C, we put complement. It's going to be the same way. And of course, F, positive, and this guy, okay, false, positive, false, okay, that would be 0.02, which is the one we have here. Look at that. True for flu, false for cough, divided by the probability of not coughing. Okay, if I know the probability of C, I can get the probability of complement of C. What was the probability of C? 0.35, right? 1 minus 0.35, that would be 0.65. I'm done. Any question? I will advise, I'm going to make this video public, and I will advise if you need more clarification, you can, take a look at that again, okay? You can take a look at that again. What I've decided to do, I committed the whole of the week to Bayesian network. We're still going to do another example of Bayesian network on Friday, because the more example we do on Bayesian network, then the more you understand Bayesian network. I know. Okay. Now, what we have been doing, this Bayesian network, if you are doing it for the first time, I need your answer. If you're doing Bayesian network, like I'm talking about this probabilistic graphical model, if you are doing it for the first time before this class, let me see your hand. Yeah, I know. It's good. It's new. It's for the first time. Yeah, and that is why 3021H is different from 3021. You know, we have a 3021. We also have 3021H. It's because you guys are smart. That's why you are actually offering this course. 3021H. It's honor. Okay. Okay. This is where I'm going to stop today. Make sure you stay safe and have a lovely day. Bye for now, everyone.